Let's get started. All right, happy. There may be a little echo. We'll see. Happy to have everybody here. This is the second of our colloquium series this semester. There's one more next week. Today, we're very happy to have Dr. Lingfei Wu from Dean's. He joined our school a couple of years ago, I guess. It's a blur because a lot of it has been remote through the pandemic. But he's doing really exciting stuff, and I'm not going to spend a lot of time talking about it. I'm just going to jump right to the meat and let him share some of the cool work that he's working on. So happy to have you. I'll get out of frame.
Yeah, thank you, Alex. Okay, I guess we'll just dance with a little bit of echo in the background. Is it because here, if I test? So what about you? This one, like this?
Yeah, let's try that.
Can you hear from Zoom?
Yeah, we can hear, and it sounds good now.
Okay,
Perfect.
perfect.
Thank you.
Yep.
All right. And we can do the version so you see some of the other people as well.
Yeah, cool. So we, I guess we have 1 hour here.
Yeah,
Cool. Glad to meet you guys. And I will start with a small life story. So I believe most of you are in your most creative years. When you're young, you are energetic with all these ideas, and as a graduate student, right? So that was me in the same stage. I was doing my postdoc in University of Chicago. And this guy you saw is called Rumberg. He's the greatest guy I ever met as a sociologist. Basically proposed the idea of structural hold to talk about identity, opportunities, and social capitals, and all the great things. So that was a summer, a few years back in Chicago. It was a hot summer. I was busy at my work, trying to identify the association between team size and innovation capability of the team performance. And then, like my supervisor by then introduced me to Rumberg, and we walked across the campus. It was hard, but that was an exciting little trip. And when we arrived, Rumberg and me and my supervisor, we met in a seminar room, pretty much like this, actually a little bit bigger. And I remember we sit on top of the chairs, the tables actually, and Rumberg is like throwing tons of crazy ideas towards me, as he usually do. Talk about excitements, what characterize great scientists, and what makes them creative when they interact with each other. So all these great ideas. And the one thing I remember from that meeting was he sent me two papers, must-read papers. And one of them is, you can see the title from here, The Old Days, Hard Groups, and Other Things. It was basically talking about expressing the author's missing of how creative MIT was when it's before the Second World War. So that was a great meeting. But I identify something from that great meeting that happens again and again in my basically entire life of academia experience. That is, whenever you visit a very senior established scholar, they always recommend some must-read paper or books to you way back to 20 years ago, 30 years ago, right? So these are, sometimes they call these classics, sometimes they call these fundamentals. But basically it's all about old days. So I now became a academia person by myself. I kind of feel relate to this. So this is what my my very personal view of what academia life is. The academia life is like, this is me. And I carry all the academic heroes that I respect and admire, and I just walk around campus, right? Sometimes I feel lonely, sometimes I don't. I feel other people share the same heroic role model with me. But in the end of the day, me is like a little time machine, right? I walk around campus, literally like pick campus, from IS building to CS building. I talk to people, my IS coworkers, now CS coworkers, and I ask questions. Do you remember some classic papers that I like? Right? This is how we talk to each other. It's like idea and classic papers are like some kind of currency. We exchange this kind of currency, like I give you gifts, you give me gifts, money or something, okay? So in that sense, each of us is kind of like a little time machine. We keep bringing our coworkers, our students, basically everyone we talk to all the great days, a historical time that I was intellectually born. That the science was, I always think science is still the same as I was trained, right? The great questions I try to hack are still great, and the most likely are not hacked, have not solved yet. The exciting methodologies I used to be so fascinating about is still exciting, it's still new. Nobody actually realized the full potential of that methodology, right? And the great persons that I respect and admire are still great, and everyone should know them. So at this point, every time when I say how I met with Rambert and talk to people and they really don't know who is Rambert, I feel a little bit upset. But this is how things happens. You know, the world evolves forward, and we kind of sticking around in some place. It's like a little train station. We wait at the train station, we hold on to the idea. Actually, we were largely trained to do that after 5-6 years PhD training. And sometimes the train just move forward, okay? So this is the setting. And with that setting, a little bit introduction about myself and my interest. So I'm Lingfei Wu from Sky at Pitt, and my interest is about how knowledge is created socially, right? Knowledge is not, I don't believe anyone can say, I own knowledge. Like you can write a paper or two or many, but you don't own it. It's like you don't own money, right? Money comes and go, idea come and go. Now, a lot of these ideas and knowledge, they're socially created and socially distributed, right? So that's like one of my most fascinating perspective of how ideas are created. They come and go. And you are like standing by, if you appear at the right place at the right time, you get an idea. You even get a publication. You even get a right code, go to write the right code, right? Now, and there's a more recent trend, we call it science of science. It's basically a rising the field with interest and the research workforce from all across sociology, business, management, physics, computer science. So that's a great opportunity to understand how science is evolving in nowadays within the historical context and what is the future of science will look like. And within that rising field, my particular interest is what's the role team plays? How can we design better teams to accelerate innovation rather than slowing down? So with that, today I'm going to introduce one single research that I'm working on. And with that single research, I will start with a single variable. And with that single variable, I'll start with a question. So this is a paper, right? That's probably one of the things we are most familiar with in the room. Is that for dollars? And there's really an association there. And that is the reference. Typically, when you write papers, you put reference on that, right? So now the question is, here in the physical room, and I'm curious in the Zoom room too, what would you anticipate as the average temporal distance between a paper and it's referenced in years. Thoughts? Quick answers? I guess. 5 years? 5 years.
It depends on the age of the author.
You mean it depends?
On the age of the author.
Yeah, yeah.
Definitely.
Definitely.
More researcher, they might remember their own graduate years and the original source.
That would be earlier also.
Yes, that's a great. And I got to stop that gentleman over there because it's spoiling alert. But you are right. You definitely get it right. But for now, like if we have average time, what would that be? So we have 5 years answer, right? Or any other guess? We do have an answer on the next page. So that's a.
So it also depends on the domain. But if we're talking about computer science, for example,
Yep.
there was no computer science in the 1900s, right?
Yes.
So early 1900s. If you're talking about physics, there are papers from 1920
Yes,
that I assume are relevant. So it definitely will depend on the domain
definitely.
as well.
So the 5 years is more like a computer science perspective.
I thought I biased for computer science when I replied. So
Definitely. I like the answer, and I'm curious about the two answers. But when I was in IS, we have more very diverse. Like some were saying 1 year, and some were saying 10 years. Okay, so I love how these people project ourselves into this question, and the answer across 244 million papers over the past 2 centuries is about 10 years. And the distribution is unimode, so we are not like we're doing crap here. We do have some kind of representative value here, right? So it's about 10 years. And Alex, you are totally right. If we do computer science, it's probably more recent, right? Basically, you are forced to cite recent conference papers like last year or the year before last year if you are submitting this year. So that depends. And then we can confirm that kind of dependency of variance between fields here. Some fields are earlier, some fields are later, and more recent, of course, historical times, there are slightly variance. But in general, the main story here, we do have a characteristic time, 10 years. People don't cite much of ideas and papers 10 years ago, okay? So now that becomes the part that gentlemen are gonna kind of revealed or hints upon, that is, we do have a characteristic value on the temporal distance of when an idea is created from the intellectual roots of the idea was created, right? That's about 10 years. Now, what if we take it as a y, and we put our career age XX, and what would it be like, right? So we kind of see several possibilities, and each of them are meaningful. And that's kind of my most fascinating part, the part I like with my job. We play on numbers, but we think about society and reality, right? So it could be a constant, right? It doesn't really, it can be like we kind of anticipate some kind of variance, but it doesn't change too much, right? It could be evolving, right? So it's like when you are more senior, because of your change of the working role, you became teacher, you teach and you instruct, and you got to keep up with what's going on, right? And you have grad students working with you. You have obligations, you got productivity expectations, so you got to keep up. And in that sense, as time goes by, you are more capable of catching what's going on in science, right? So that would be an evolving scenario. Alternatively, it'll be just aging, but you still try to catch up. But still, you have a huge gravity towards the past achievement and the things that you were excited about when you were trained as a PhD. So we don't really know. Now, as a scientist, we test the things we don't know, right, and try to discover. So this is what universally it looked like when we analyze 1 million scientists with a career age of 20 years or longer, so we can really go with a very decent analysis of career-wise research strategies. And that they are picked from over 200 million people who ever published in the past 200 years, provided by Microsoft Academic Graph dataset. So what we see here is a universal line that provides the first very large quantitative evidence of aging phenomena in science. Right? Now, this is the average of everyone, right? But we always want to know what's the more like rich stories. Now, what kind of things can it change with this? Can we just observing some kind of average trend, but we will break it down to people of different historical times, people of different career length, people from different fields, it kind of dissolve. There's no such thing. It's just average illusion. Can it be like that? So we try to explore this pattern again and again from different perspectives. Now let's think about one very dominant thing that differentiates people when you peak, right? So in science, some people peak early bloomers, and they basically publish the most definitive paper in the early years. And some people are really late bloomers. So Einstein is famous for his like gold years when he was so young, right? This is a young photo. And so basically what we analyze here is like, we take these 1 million people, we take them out. If they publish the most cited paper in the first 5 years, which indicate by the little star here, and we separate the line, right? So they are still aging, but they actually aging even a little bit faster than the average people. Why? One possibility is because they have such a great achievement in the past. There's a whole gravity towards that achievement. It's very hard to fight against that achievement. Like if you publish papers that talk about general relativity when you are 30, like you cannot not talk about that when you're 40, right? Now that's confirmed by drawing upon this statistic from these late bloomers. I mean, to be fair, I don't think Geoffrey is like pure late bloomer. He's late, have great papers every a couple of years, right? But if you look at the literally just like the most cited paper, and that's a lot of that was from recent years. Here we define late bloomers if the most cited paper of you is published after 20 years of career, from the first paper. So they're actually aging less. Okay, so when do you peak? Doesn't really change that, although add a little bit to the richness of the story. And we explore other directions. It doesn't change with career length. Either you spend 10 years, 20 years, 30 years in science. It doesn't change much with historical times, 90s, 80s, 70s, 60s. It doesn't change very much across disciplines. But indeed, although all disciplines, people aging, there are like some disciplines I would like to call code, in which you have more privilege to age. But in mathematics, you can still cite papers many years ago, and you are legit, you can still publish. And largely because it's the tools, the problems are still there, you still can use them, right? And in engineering, biology, medicine, and of course, most relevant to us, computer science, it's very hard. It's a hard field. People come and go, idea emerges, problems emerge and solve quickly and emerge again. So these are like hard fields that you got to catch up or you're out. Okay, so what we see here, despite the richness of layer by these different perspectives, when you peak, how long you stay, and what kind of work, what kind of knowledge you are working to produce. But the universal trend is people age. Now, what kind of mechanism is really behind that? Why people age? When we calculate it's just average number again, right? So I put out my own publication records to understand that better. So this was me. This was the first paper I published when I was a PhD. I was trained as a social scientist, but I never want to stay like that. I was so fascinating about physics, so I worked with physicists and learned methodologies from them. I published my first paper in European Physics Journal B. That was 2011, and we're talking about modeling online tagging systems with its scaling properties. And that paper was largely inspired by Barbashi's paper on 1999 in Science, talking about the scaling properties and how does it evolve from the preferential attachment model. Okay, so that becomes one of my cornerstone of thinking. I think everything in that paper, right? Of course, and a couple of other papers that defined network science. And I don't know whether it's good news or bad news, but when I try to put out one of my recent papers, I collaborate with a PhD student from University of Chicago, and it's a very interesting sociology journal, Poetics, very nice name, on empirical cultural phenomena. And in that paper, I am still citing Barbashi after 10 years. So what I infer as a dynamic from this picture is, so that was me, right? I was intellectually born in 2011 in the data, and by my first publication. And year after year, I publish more and more. But I always go back to the place that I feel excited, right? I talk about new problems, but then I talk about new problems in the way that I can understand or I can help, which was defined by key papers when I was young, right? So that dynamic, I call it like, in some sense, I call it a preferential return in time. You keep going back in the time, then you are excited, then you are trained, then you're like you intellectually build it, right? And this is confirmed when we analyze again million level scientists. We ask, we didn't really talk to them, but we kind of ask the data, what is your most frequent reference in the whole career? And we believe that kind of reference actually just define your thinking, right? And we confirm that it's a long tail, right? People keep repeatedly cite one reference again and again. And while most of other references appear 1 or 2 times in all publications, and a lot of them are actually strategic, it's just to show relevance within the field, right? So the key paper that most cited in Korea is peaks before one's first publication. But that provides evidence that people kind of keep referring back to the science that they were born into, right? Now, why is it important? And what kind of things it triggers? What kind of opportunities it provides and what kind of challenge it leads to? Well, this phenomenon really reveals essential tension in our career academic life. Now, let's think about what is science. Science, there are 2 kinds of science, right? One kind of science is what we teach. We teach science in the way that this is computer science, this is physics, this is math. That's like a library science perspective of science. That's how we put science in the shelf, how we remember that, how we sort things out. So that's cold science, that's dead science. We are talking about science that in the past years, right? That's teaching. But there's another kind of science that we all engage in. That's ongoing science. The grant proposals we need to write, the conference things that we need to respond to get published, and the ongoing things, like when COVID comes, we need to say something about COVID. That's the society expectation of what scientists do. And although, so everyone try to dive in to the pool and contribute to COVID's solution and the prevention and everything. That's ongoing science. Although there's no something called COVID science in our shelf, and there's no something called poverty science problems in our shelf, we solve it. That's the real problem-driven science, right? Now, problem-driven science keep moves because society changes and new problems come up, and scientists are rewarded to solve these problems. If you solve them, you get grants. You get grants, you maintain a team, and you supply next generation scientists, right? And so then we got new problems, new phenomena, and we call it hot demands from society that you need to respond to. So that's either innovation, obligation, or expectation on us. In the other way, when we think about the supply side of knowledge rather than the demand side of knowledge, we have this kind of preferential return. mechanism that happens, right? We were trained to get familiar with theories, with some machine learning models, with some regression models, with some solutions. And that's how we train as a scientist. Now that becomes to a little essential tension here. The way we train and the way we need to work upon does not always align and or keep changing, right? So that becomes a problem. Like if everyone is aging, how are we going to respond to the ongoing science? And how new science, new ideas can be used to build future science, right? So that really opens that a bigger picture here, which I visualize as an innovation clock metaphor, in which you have the whole landscape of science. Here, each dot means a journal, and I took just 10,000 journals in the data set, and I do the embedding of them, use neural network embedding technique, which I believe most of you are very familiar. Basically, two journals are close to each other if they appear a lot in reference, right? So they are relevant. And you can project a high dimensional 300, 100 dimensional representation of that journal or whatever you want to encode into a two-dimensional by some kind of data visualization algorithms. Okay? So here we see what's the whole landscape of science. Right? You got social science here, chemistry here, and biology here, medicine here. Fields of relevant knowledge are close to each other. And what I'm a little bit other things I do is I place clock on those things. And that clock, I have only one leg or hand, whatever you call that, in the clock, pointing to the average reference age in that field. Now, that interesting thing comes up, that is when you have very relevant knowledge, like computers and computer science and mathematics, right? They are related to each other, but they actually live in a very different kind of innovation clocks. In mathematics, you can cite the 30 years ago paper, 13, right? Totally legit. In computer science, 7 years ago sounds suspicious. Right? So it's like, I mean, like, so that's so fascinating to look at, right? When you are a PhD student and you are like going to think about your life, career unfold ahead, and that's a hidden dimension to think. Are you the kind of person you want to move fast? I mean, some people are just capable of doing that, right? Or are you the person who you prefer to have a more slow pace, slow thinking, but hang on to ideas and keep solving it year after year, right? So that's something to think of. And to really feel that I just have too much time on this project that I suspend, I did a visualization of to show how science look like. It's just so each of these is a subfield. We have 200 and more subfields, and each of them are like are just like clocks working in the different pace, right? Try to nudge us of publication obligations. Okay, so for that, basically, like anchors my main story. That's reference distant thing. But at this point, I know you are all well-trained scientists. So you may raise question, can we just dangerously tie the whole big story with a single measure? What if that measure doesn't, well, you can cite things that many years ago, but it's fundamental, right? Why we shouldn't cite old things just because they are old? Maybe they're old good things we can keep citing. So to really respond to that kind of concern, we do look at this story from different perspectives. So here, at the right figure, we look at, we take one's publication out and we separate by field, right? And we identify the home field of these scientists if they publish 0.5%, 50% or more paper on only one key domain that we identified. And then now you have a home domain, right? And then we analyze every year of your publication, they take the keyword out. That keyword is constructed by Microsoft Academic Graph. It's a giant scientific concept taxonomy, right? We take that keyword out so that describes what you are doing in this year. And we also analyze what's going on in the field. So we take all the people in the field in that year and take the top 1% keyword out. So what's the trending word? Just imagine Twitter trends, right? And then we calculate the match. So at first, right, when you are intellectually born, you are so relevant to the science going on, right? Whatever you do, you just do the fancy things. You're basically just working on the scientific Twitter keywords. Now, year after year, after another year, after another year, you kind of stick on your familiar topic, and you are distancing away from the field. What's going on in the field? Okay, across all fields, no matter what field you are in. Now you may still ask, well, you only observe the distance, but could it be me change or could it be the field that change? Right? We don't know. It's just like it's a relative distance. So we analyze one against themselves, and do confirm that year after year you basically work on the same thing over time. So you didn't change, the field changed and move forward. So that's a complement perspective of the story based on the temporal distance. We look at the content, the keywords that kind of support the same story. And we look at a couple of other dimensions, like disruption is one of my recent paper published on Nature in 2019, talking about measuring how one paper cites, the future paper cites the focal paper, but not its reference. So it's an indicator of to which extent a new paper shifts the path of science, rather than continuous the ongoing string of science, right? And that's an indicator between negative and positive one. And you really observe as time goes by, people are less and less likely to shift, to change, to challenge the field and make it a new direction, right? And we also do some like very classic computation, social science perspective. This is called a fixed effect model that basically construct to ease the concern that we are not talking about scientists themselves, but we are talking about different kind of scientists across different time, different level, different fields. And this is called multi-level hierarchical linear regression that controls everything and kind of still show the key effect. Here. Somehow it's, I need to just, sorry, 1 second, I'll just need to put out this. You can see the coefficient is 0.1. So it's still the same thing. Like basically every year you are aging, you got aging every 1 month aging after control everything. Right? It's even bigger than you don't control things. So what's the policy consequence? Okay, I mean, it's fine to make a dark story, but I don't want to stick with the dark story. In social science or computational social science that I identify myself in, we seek for policy consequence. So what we learn from here and what are the actionable items from here, right? So I care about teams. Now, what aging phenomenon tell us about teams is we got two choices, right? Like senior and junior scholars. You can either team up or you can either just separate. So what kind of consequence will happen if we look at these two? Let's start from what happened when they separate. So this is a typical one paper, a big paper in social science that published on Science. The same pattern repeats for other papers. So we just pick this paper here, and you analyze all the citations to that paper, right? So this is a very classical bibliometric thing that we should do, one can do. But the non-typical thing here is we combine that with NLP techniques. So we now can identify when people cite other people. Are they citing happily or unhappily, right? And it's actually more dedicated than that. But I think you are all experts. You kind of get the function classification kind of analysis that we know when people cite other paper to criticize or cite other paper to agree, right? And the interesting thing is that you find these two kind of citations really separate in the in demographic age, right? So this is the average. The black dot line is the average career age of the team members, and you basically find when this paper was published or after it's published, all the people who just older than that paper are more likely to cite and disagree that paper. And people who are like younger than the paper just decide to celebrate that paper. This is such a great paper. This is the best paper. At this point, I think it's fair to bring in, sorry, I keep forgetting the title of the movie. 2001, The Galaxy, what's the full name? Yeah, exactly. And in the original book, there was a famous quote, right? Everything that invents, when you were born, it's kind of part of nature, part of that world. You never imagine how they were created. And everything that was invented when you were teenage, you were like 15 to 30-ish. It's kind of so exciting. It's kind of revolutionary. And you probably can seek a career opportunity from there, right? And anything invented after, I'm now dangerously 35. After 35, it feels so unnatural and against the law of physics, right? So I mean, I don't want to exaggerate, but I don't think that captures everything. But it does capture some kind of human tendencies, and which originates probably because our limits bandwidth of capacity, memory, and emotional capital, right? Everything. But this is what we found evidence in science, and how people do science does some kind of echo with that famous quote. People just don't like new things and stick to the things created when they were young, right? And this phenomenon is quite universal. We start from one case, and you can observe the age gap underlying the critical citations, and you put out all the millions of critical citations and analyze the distribution. Now, if the distribution has an expectation of 0, I mean, it's kind of people just criticize for all kinds of reasons, and that cancel out. That shouldn't be biased, right? But turns out people are indeed criticizing things that from people who are younger than them, right? So there's a symmetry distribution across all fields. And you will analyze that the fraction of papers, including at least one criticizing reference in your annual product paper, it just increased all the time, right? So this is what happens when we separate them, right? Like different generations, they hold on to. There's no right and wrong here. This is human tendency, right? And then different generation hold on different generation of important ideas, and then they disagree with each other, right? And so this is kind of the demography perspective of a paradigm shift. And the good thing happens when we try to mate them together, and basically when you have young collaborator, which is good news for our computer science coworkers, because we always have so much energy and so much young souls here. So when you collaborate with people younger than you kind of reset the innovation clock, right? You're forced to care about recent things and cite recent reference. And of course, when you move across places to new institutions, when you intellectually move to new places to study new topic, you kind of do the same thing. But in the end, it's a people story. It's about people interaction. So, and that confirms with our data that working with a young collaborator is brings the most dramatic change with your intellectual aging. Right? So that's the main results here. And then at this point, I like to bring this even bigger and try to answer the question, what kind of ongoing big narrative this is talking to, right? So there are several ongoing big narratives going on in the science of science. One observation is the idea are getting harder to find. Many are talking about this. Citations are getting less exciting as they used to be, but it's probably not just an aging complaint, right? It's probably something real. Confirmed by recent prestige academic papers on idea production. And this is our result. We confirm that across all fields, if you have more aging proportion of people, which can be defined as people, the fraction of people have 20 years or more career length, then the churn rate, which is like, this is the metaphor, but basically the chance that the keyword of the next year will be different from the keyword from last year, right? That kind of churn rate will be slowing down, right? And there's a paper, there's a recent narrative about the slowing progress in large fields. So that basically talks about when a field becomes very large and there are too many voices at the same time, and people just prefer to ignore all of them and just listen to the old voice from the canonical classic literature, right? And this is confirmed with our results that across the past century, across all fields, human science are more likely to cite earlier paper than recent paper, either calculate by mean age or of reference, or just calculate a fraction of new reference in papers. So that does enhance that concern. The rates new idea get to be used to create future science is slowing down. Right? And then one last concern here is a recent study on the US scientific and engineering workforce is aging, right? Especially in comparing to other Asian countries and Europe countries, right? Mostly Asian countries. So our result does confirm that over the past century, the fraction of old scientists defined again is 20 years or older is significantly increasing, right? So science is more created by aging scientists rather than they used to be. And especially when you look at the prestige journals, they're more and more dominant by people who already published there before, which is called chapter one effect, and also like just in general, experience speaks louder and louder in science, right? So I'll end up here, but bring you close my talk with a narrative that I called reinventing scientific talent, right? So basically, we see all these kind of anxieties from aging academic workforce, from referring to slowing down rates of using new ideas and new discovery to do future science. And we do have positive evidence from teams that greatly combine the senior and the junior scholars. But what is the frameworks to understand everything here? One framework I like to propose is how do we see and what should we do with scientific talent, right? So what is scientific talent? It's one thing we need to understand is that it grows very slow. Like you have 100 computer scientists graduate from US last year, and that number is not going simply to be 200 next year, right? It grows very slow, and especially for high quality program like what we have here, right? So you can't just double and triple that every year as much as papers, right? Which we know papers just exponentially increase, but scientific workforce itself grows very slowly. Now you can't change all of a sudden just change double everything. But what we can do here is to rewiring the connection between these talent, right? To match excitements and energies with experience, to put diverse people together, and that just create double and triples the innovation capacity we have as a society and as a nation. Okay, that will be my talk, and appreciate your attention and welcome questions.
We have time for some questions. We can start there. No, no, you sit there. Let me bring the gallery up if there's something from. The active ones. So any questions from the audience?
Yeah, so on the chart that showed the last set of charts showing the average, the percentage of old scientists. Yeah, yes, this. So it looks to me in a couple cases like the charts actually, the line is actually starting to flatten out as we get closer to the present day, and that makes me wonder if there's some effect since we can kind of agree that 1960 is the beginning of industrialized modern science with modern academia. It makes me wonder if in the future all of these lines might just flatten out, and that just might be the fraction of established scientists. What do you think about that?
Yeah, that's a deep question. I need more time to think about that to effectively respond. But I agree that I will just quickly anchor with one of your keyword, industrialization of science, if I get it right, right? To what extent does this curve project to the next following years, even just decade? It's a big question, but I does echo, feel very agree with your observation that nowadays science is done in a very different way than like 50 years ago, 100 years ago, right? There was a time driven by individual scientists, by heroes, by talent. And nowadays we call it scientific enterprise. Grant money is the most driven thing in all these big giant scientific project teams and institutions. And so my contribution to your question would be why experience are getting more important in science. That could be one of the reasons. When you from small science to big science, science evolves a lot of management part, right? Like when science was young and when scientists were young, young people have more time, old people have more experience. Now you have some kind of scientific problems like mathematical problems, programming problems. On that kind of problem, you spend more time, you try more times, you're more likely to make achievement. So that's why we see a lot of great achievement in mathematics, in physics, were done by young people. But it's rare to see that in humanity, in history, in philosophy, or in social science. And that's because in this kind of domains, knowledge are more like socially storage and created. And this relates to the switch from individual science to big science, to small science to big science, in which we just need more experience to maintain large groups. So that's probably a relevant thing. And I personally don't want to see a flat line or increasing line, but it's interesting to learn more from there. Yeah, I like that question very much. Thank you.
Good.
Please. Oh, that's very sharp. Yeah, this is a group that I need to be more prepared, showing every single panel of. So yeah, let's explore it a little bit. So after 2000, indeed, there's a more recent driven thing, right? For biology too, kind of, and for medicine, right? So, oh, that's a very sharp observation. I've been looking at this figure many times. I never. Yeah, so okay. That one hint that one hunch I can immediately capture is probably relevant to technology or machine-driven or machine learning-driven kind of discoveries. I kind of know that in all these fields, biology, chemistry, and medicine, we have seen a lot of like new technology applied to that. It means the way knowledge is created and the business is done is shifting. That's probably a relevant part. And one way to explain that, to explore that I would like to do is probably we separate journals that's more relevant to like methodology against journals that are more relevant to theory, right? And then for that, we see more methodology journals contribute to more a little peak of applying recent ideas. Yeah, that's true.
Panos first and then Pano. All right.
Yeah, it would be interesting to see what is after what was done before internet and what was done after internet.
Yes.
I think many of them are rather downward trend because after internet, the information access journals or paper or the scientific information was much more easier. That's what I think.
Yes.
Happening. And previously it was all in paper and everything, and then the references were more exciting because you had to go through all that stuff. Nowadays, you just do research, not the keyword.
But we're For example, you may not know, none of you may know this, but way back when there were technical reports that department would have, and people would call and the department would send the technical report, and that was one way that way back when the conferences, the way they managed papers were physical copies of papers being mailed. So I have stayed overnight to make a 9 a.m. cutoff, same day FedEx delivery to meet the conference deadline. It didn't go through, but so things definitely have changed. So Panos, and then I may have one more after.
Yeah, definitely.
Actually, I was going to compliment what you said. First of all, let me go back to what at this point we have the new trend in the development. We have the computation, physics, and I wouldn't be surprised when we move to take humanities now and to see computational social science, computational political science, so on, to see new trends, because this changes the name of the game. This is related also to what you have said. Without the internet, the digital libraries make democratize, let's say, the accessibility to the literature, but they have created also biases.
Yeah.
Because now, actually, I would be interested to see whether now some references will attract more and more because they became more popular. It's like ranking. And now we will see a different kind of bias in creativity and how attributions and so on is going on.
Yeah.
So, yeah, I think it's interesting to see prior internet and post-internet and compare the two. Things have changed.
Definitely. That's included. That's the working plan. And just a quick response to that. That's a great opportunity here, and I welcome continuous thinking on that and the conversation. I mean, you can just walk across the blogs because we have talked a lot about information cocoon, right? Like how social media just provides a great potential for you to reach out, but you don't actually do that all the time. You're actually constrained in whatever you like to stick with, right? And I'm always curious and excited think about that in science, like you said. Now we have much more capabilities to communicate and search. You also said that there, but that's a potential. But to what extent does we translate the potential into realization? We actually search broader and read more than our earlier generations. That's an interesting question. Yeah.
I have one quick comment too. So there are some disciplines where the size of the usual collaboration is different. Like astronomy, for example, you would see 200 authors in a paper. I'm sure they're going to cite their own work, so that the type of graph is going to be different. So that's the one thing that maybe can be filtered further. And then another observation here also is, I know in the database community, for example, the predominant, and almost all of computer science too, the conference is the predominant. And then usually there is a page limit that includes the references. So people are restricted by how many, so there is restrictions in the page number, therefore it restricts the references. Journals sometimes have page limit, but oftentimes they don't. So then there is no limit on the references. So you don't have to choose because things don't fit. You can, and now some of the conferences also said, well, there's like 10-page limit for the paper, as many references as you want. So these are some kind of other type of artificial constraints. So some of the paper venues have constraints about how much you can cite, and some don't. And I think that probably affects some of this.
We explore both. So the distribution of the reference length is kind of unimode, around 20-something, 25-ish. So that doesn't really change things. But your first point is excellent. We look at that, and the fields of bigger teams, I mean, computer science is kind of on the bigger team side in compared to mathematics and sociology, they just age slower. Because on average, to assemble bigger teams, you need to include young people. So excellent comment. Thank you.
Any last thoughts, questions?
Anyone?
I have a question.
Go ahead, Doug.
So I was thinking about when you commented on how basically science is like getting harder, slowly and slowly getting harder. And it reminded me of in undergrad how some of the math professors commented that fields like topography are getting harder to get into or make progress on. And like a lot of people are going into fields like graphs and graph networks. So I was wondering, did you do this same analysis within field? Or a similar analysis within field. So like in mathematics, you could break it down into graph networks, topography, numeric analysis, and so on. Or computer science, you break it down into databases, OS, and so on.
Yes, we did that for subfields, 258 subfields across 11 fields. So it's kind of still same pattern.
Still same pattern, okay.
All right, so let's thank the speaker.
Yeah, thank you all of you.